Hello everyone, my name is Karol Hausman and I'll be talking about unclogging robot learning. So this RSS workshop is about structure and structuring robot learning. And I think there are these two separate views on structure. More traditionally, structure can be viewed as something where if we start from some chaotic line of thought or some phenomenon that we see in nature that we don't really fully understand, discovering the underlying structure allows us to understand it better and then to replicate it. This is how a lot of engineering fields have been making a lot of progress. However, there's also this other view that is maybe a little more recent. Let's call it the data-driven view, where if we imagine that our data is water going through a pipeline, and the pipeline is the minimum structure that is required, then we are trying to optimize the throughput of that pipeline as much as possible. In that case, structure can be viewed as something negative. So if we put too much of it, it might clog our pipeline and we won't be able to use as much data as possible, and we can't have as much data flying through our pipes. And because of that, we won't be able to discover the right structure. So let's take a look at these two views in more detail. In the structure-driven view, we have this equation where if we have enough data and we discover the right structure, we should be able to solve many different tasks. One example of this is classical planning algorithms, where we have the data and the right structure to represent the world around us and the right structure that is embedded in the planning algorithm. If the planning algorithm is correct, we should be able to solve basically any task as long as the structure is also correct. In the data-driven approach, the equation looks slightly differently. When we have enough data and a broad enough task, then structure is something that can emerge from it. An example of this can be seen in the ImageNet dataset, where we have a lot of data, a broad classification task, and a very capable neural network model. And then if we train it on this classification task, we can use the features that the model has learned to solve that task and reuse them for another visual task. In the structure-driven view, structure usually amounts to more efficient learning. We can bring back the same example of motion planning. And here, if we're faced with a new situation that we haven't seen before, as long as the world that we see is represented correctly, we don't even require any learning. We can basically just apply the same algorithm, and in zero shot, it should be able to solve this new task. In the data-driven world, we don't really worry about efficiency. We are kind of sweeping it under the rug for now. And we have these robots collecting data all the time, multiple of these robots, and we kind of don't worry about this for now. In the structure-driven view, there's no reason to relearn things that we already know how to do. So for example, we are the ones designing the robots, and we know how motors and gearboxes and kinematics works and so on. So there's no real reason not to model this because we know how they work. In the data-driven view, however, we would like to put as minimum structure as possible so that we can use as much data as we can. One example of this is the interest and a lot of progress in unsupervised learning algorithms that allow us to tap into data sets where we don't have labels. We also see this in reinforcement learning fields where we try to approach reinforcement learning problems by tapping into other data sets, such as the vast data set of YouTube videos to learn how to explore. And then lastly, in the structure-driven view, most of the progress from the field comes from our own ingenuity. So basically, we hope that we'll be able to discover the right structure, and better models, and from that, we'll be able to solve more tasks and do it better. In the data-driven view, there's also another line of progress, which just comes from scaling things up. If we can just pour more data and make our models bigger, we can make a lot of progress. This can be exemplified, for example, in language generation, where the GPT-3 model published by OpenAI was able to achieve state-of-the-art performance. And the main contribution of the work was basically to make the model much bigger than the previously known models. All right, so in this talk, I would like to take the data-driven view and see if we can transform robotics to kind of be in that regime. And what would it take? So first of all, I would like to test whether this equation that we've seen succeeded quite well in computer vision as well as in language also holds true in robotics. So if we have enough data and a broad enough task, can there be some emergent structure coming out of this that we can reuse for other tasks? Also in this talk, I won't be focusing on the efficiency of learning. So as according to the view, let's worry about it a little later. And I'll be trying to show methods that allow us to put more structure into the problems, but not necessarily to improve efficiency of our algorithms, but rather to unclog that pipeline. So basically to allow us to use as much data as possible. And then lastly, robotics is somewhat a peculiar field where generating data is actually really difficult. And we can't just look at YouTube videos only. So in this case, I'll be also talking not only about how we can make that pipeline have very large throughput, but also how can we generate enough water that goes through those pipelines. So how can we scale up our data collection process in robotics so that we can use the data-driven techniques? And the hope would be that if we do all of these things, and if we do all of them correctly, we'll be able to make progress in robotics, similarly to how other fields have been doing it recently, such as natural language processing, computer vision, or speech recognition, where we can get a lot of progress from just scaling up our data and our models. All right, so this is the outline of my talk. So let's start by trying to answer the question whether task plus data can equal some emergent structure. So just to remind everyone what we are focusing on here, in computer vision, we've seen this phenomenon that if we have a big enough data set, such as the ImageNet data set, and if we have a very capable model, such as a big convolutional neural network, and we train it on a broad task, such as the ImageNet classification task, we can reuse the features that were learned during that process, and then repurpose them for any other visual tasks, and they work fairly well. So we can try to see whether the same kind of dependency we can also see in robotics. So in order to do this, we need to take advantage of a big data set. So here we'll be taking advantage of the data set that was generated in this paper called QT-opt, developed by Dmitry Kalashnikov et al., where we had 7 robots collecting data over the course of a few months. And also they were collecting grasping data on a very diverse set of objects. So basically it's not only a large data set, but it's a very diverse data set. And I would argue that the task of grasping is kind of as broad as the classification task is computer vision. And we are also sure that this data set kind of makes sense, at least to some extent, because if we use that data set and try to learn how to grasp from it, we can actually achieve 96% success rate on unseen objects. So it seems that there's a way to make sense out of it using policy reinforcement learning. All right, so let's try to replicate this procedure that was done for computer vision. So we'll take this big data set. We'll have a very capable model, a very large model that was trained to achieve that 96% success rate. And then we'll see whether the features that we're learning that model can be reused for another task where the model is not that good at. All right, so in order to do this, we developed this method. This is the work led by Ryan Julian, which is a very simple fine-tuning method that would allow us to test this hypothesis. So it works very simply. We start with the pre-training task that was trained on 600,000 grasps. So this is this QT-opt data set. Then we pick a fine-tuning task where the algorithm doesn't work that well. We collect only about 4 hours of data for that task. This is less than 800 grasps. So this is a small fraction of the original data set. And then we have a simple adaptation procedure. And once we do that, we can evaluate this new policy in that fine-tuning task and see how much can we improve, if at all. So the adaptation procedure works as follows. We have the pre-trained data set, as well as our target data set that we're fine-tuning to. We first train the Q function using the QT-opt algorithm using the base data set. And then we create this mixture It's a 50% mixture between the target data and the base data. And we use that new data set to fine tune the model that was already trained using the original base data set. This is depicted here in step number 4. Once we have this adapted Q function, we'll evaluate it in the new scenario. Right, so given that simple procedure, we first had to find the right fine-tuning cases. So for this, we have the baseline model that was basically the QT-opt model, but evaluated on a specific set of objects that yielded 86% success rate. The fine-tuning scenarios are as follows. First, we have harsh lighting conditions. So we have this industrial light shining directly into the bin, causing all kinds of shadows. That drops the success rate to 32%. We have adversarial objects, such as transparent bottles. This causes 49% success rate. And then also different backing on the bin. The one that was particularly bad was the checkerboard backing, where robot tends to grasp at the edges of the checkerboard as opposed to the objects. We also changed the morphology of the robot. So we extended the gripper by 1 centimeter. That only resulted in a small drop in performance. And then we also offset the gripper by 10 centimeters to the right, causing the robot to completely lose its aim. So that caused a 43% drop. Right, so let's take we collect data using on all 5 of these scenarios up to 4 hours. And then we use our adaptation procedure and we see how well we can do. So here's one example of what's happening. So on the left, we can see the original model that was yielding 43% success rate. And we can see that the robot has really bad aim. I mean, the gripper is offset by 10 centimeters. It's even difficult to recognize that this is a normal industrial arm. On the right-hand side, we can see that after 4 hours of fine-tuning with a very small amount of data, we can basically completely solve the task, achieving the result of 98% success rate. We also compared it to an ImageNet pre-training to kind of see how important it is that pre-training is done through reinforcement learning. When we do that, then in multiple scenarios, we get rather unsatisfactory results. In this particular one, in the harsh lighting scenario, we only yield 2% success rate. And whereas if we use our reinforcement learning pre-training and fine-tuning, we get up to 63% success. All right, so looking at all of these scenarios, we are able to see that we can significantly improve in performance in every single one of them, sometimes more than 2 times. And just to remind everyone, this is just using less than 4 hours of data in each one of these scenarios. So this seems to indicate that it is possible, so that the original QT-opt network was able to discover some kind of structure about that task that we can then repurpose for a completely different scenario that we are not really good at. And since it worked once fairly well, we also tried to test the hypothesis whether we can do it multiple times. So this is basically a continual learning case where we can retrain a single lineage of policies repeatedly. So we basically start from our pre-training data set, then we collect 4 hours of data in harsh lighting conditions. We train on that, then we take that network, it's further fine-tuned with the transparent bottle scenarios and checkerboard backing and so on. And looking at the results, we see that there is no significant difference between these results where we are fine-tuning multiple times versus where we fine-tune only once. So this seems to indicate that this could be an interesting continual learning method that is extremely simple and that can adjust to ever-changing conditions. All right, so a few insights that we got from this work. So first of all, we see that fine-tuning for control seems to work. So it works similarly to how it works for computer vision or for language tasks. We also notice that reinforcement learning pre-training on a broad task is key. So we can't really replicate this result with any other pre-training. And then we also demonstrated that this works also in a continual learning case. All right, so with this question out of the way, I would like to focus on how can we get some kind of structure in this problem, but a structure that will allow us to use more data. So in particular, I think there are two aspects that would significantly improve our ability to work with very diverse data sets and kind of allow us to use much more data that we are currently using. So first of all, I think we need to have algorithms that are able to deal with off-policy data sets. And this would allow us to basically take advantage of data sets collected by different robots for different tasks and so on. And that would allow us to scale up the data that we can use. And here I would encourage everyone to take a look at the renewed interest in offline RL, which is kind of an extreme version of an off-policy reinforcement learning field. And I would encourage everyone to take a look at the tutorial here, as well as the new benchmarks that were introduced, and there are a lot of exciting progress in this area. But then I think it's also really important for us to have algorithms that can deal with data that comes from multiple sources. That means multiple environments, different tasks, and different robots. And in this particular talk, I'll be focusing on multitask reinforcement learning that deals with data that comes from many different tasks. All right, and when we started looking into this problem, into the multitask reinforcement learning problem, the first thing that we realized is that there are no really good benchmarks for this. So there are multiple benchmarks that are fairly successful in reinforcement learning, such as the ones listed here. And they provide a lot of different environments. However, these environments, they don't really share a lot of structure that would allow us to kind of have multitask reinforcement learning algorithms discover that structure and take advantage of that. So to deal with this problem, we propose our own benchmark called MetaWorld. This is a fully open source benchmark that proposes 50 different manipulation tasks already implemented in MuJoCo, where we have a Sawyer arm that is doing different manipulation tasks that are listed here. And the key here is that these tasks are all manipulation tasks and they share a lot of structure. So we hope that if we train all of them together, it will be better than the sum of all of the parts. Not only we propose these tests, but we would also provide some evaluation protocols. So how you can evaluate multitask reinforcement learning algorithms with either just 10 tasks, the data set called MT10, or all of the 50 tasks called MT50, but also meta reinforcement learning tasks, where you can test the performance on an unseen task. All right, so we prepared this MetaWorld benchmark such that every single task is completely solvable with state-of-the-art reinforcement learning algorithms. That's how we made sure that the tasks are correct. And then we tried the multitask version of these algorithms, and the results are kind of alarming. So what we saw is that even though on the MT10, so on 10 tasks, we are able to get some version of the algorithm, of the multitask RL algorithms to perform fairly well, the MT50 results are very low, given that we can solve each one of these tasks individually. So we started asking the question, why is that the case? So one hypothesis could be that it's an exploration problem. However, that doesn't seem to be the case because all the tasks are solvable individually. We also thought that maybe there's not enough data, so we let the algorithms run for much longer, and that we noticed that the performance just plateaued at a certain point, and we didn't see any improvement after that. And then we also thought that maybe this is a much harder problem, so we need a much larger model to represent that result. And we made a model an order of magnitude larger, and that didn't seem to help either. So all of these led us to believe that maybe there's something about the multitask optimization, some core optimization problem that makes this much more difficult than a single task case. So this is how we came up with the algorithm called PCGrad. This is work led by Kevin Yu. We first started with 2 tasks, and we started plotting the gradient cosine similarity between gradients coming from one task and the other. So here, if the gradients of 2 tasks agree with each other, then the cosine similarity is equal to 1, which means that they're pointing in the exact same direction. And if it's -1, that means that the gradients are pointing in completely opposite directions, meaning that they're conflicting and trashing each other. So looking at these 2 tasks, we can see that the gradient cosine similarity is jumping from -0.75 to plus 0.75 all the time. So it seems that the gradients are conflicting all the time. So we came up with this very simple optimization algorithm, which basically says that if we have two gradients that are conflicting, we can project each other onto each other's normal plane. And if they're not conflicting, we'll just let them be. We don't do anything. So it basically works like something like that, where we have conflicting gradients, we project them onto the normal planes. And if they're not conflicting, we don't do anything. So first, we just had to do a sanity check that the algorithm is doing what it's supposed to be doing. So looking at the gradient cosine similarity plot from before, we see that all of the gradient cosine similarities are now greater than 0 because PCGrad removed that trashing gradient. And then we also tried it on a simple toy problem where we have this multitask objective. We have these two different valleys and they both merge at some point. And at the end of that merged valley is the global optimum. So that's where we're trying to get to. So we have task 1 objective, which is the valley on the right, and task 2 objective, which is the valley on the left. And if we start in one of the valleys, we notice that using a simple Adam optimization algorithm, we are not really able to solve this task because of the conflicting gradients problem. However, using PCGrad, we are able to reduce the amount of conflicting gradients and solve that task fully. So somewhat encouraged by these results, we tried it on the MT10 benchmark. So let me describe the results that we see here. So in yellow and in red, we see different versions of multitask reinforcement learning algorithm here. This is a soft actor critic algorithm. And we can see that it can achieve up to 40% on these 10 tasks. And then in blue, we also see the independent results. So this is if you train the tasks individually. And as I said before, we can solve these tasks fully. Now, if we apply PCGrad, we see that not only we are able to solve all of the tasks, so basically match the final performance of training them individually, but also we can get there much faster, indicating that training these tasks together actually allows us to discover the structure, and the discovery of the structure helps with training all of these different tasks. We also see very similar results in the MT50 benchmark, which is a much more difficult benchmark where you have to solve all 50 tasks at once. Since PCGrad is a simple optimization, multitask optimization algorithm, we also applied it to a supervised learning case where we are solving multitask supervised learning scenarios. And in the two scenarios we applied it to, we're also able to achieve state-of-the-art results depicted here. All right, so to summarize the results in PCGrad and the key insights. First, I think we need a better understanding of multitask optimization. This is a fairly simple algorithm that we introduced that seems to make quite a bit of a difference. We go a little bit into details, into theoretical details in the paper that I encourage you to take a look at to see why this works so well, but I think we need a much better understanding of why that is the case. Also, any improvement in that area will directly influence fields such as meta-reinforcement learning and many other subfields, since a lot of times the bottleneck is actually multitask learning for those. And this is also an example of how we can work on structure that allows us to use data from multiple tasks. So it will potentially allow us to tap into data that comes from many different sources. All right, so in the last part of the talk, I would like to talk about a scalable way to generate more data in robotics. And in order to do this, I would like to talk a little bit about supervision. So in computer vision, we started with this ImageNet data set that had a lot of labels, and we're able to achieve really good results using supervised learning. But more recently, in vision, we started seeing the emergence of models that are trained or that are pre-trained completely unsupervisedly, and they're able to achieve as good results as the supervised learning counterparts without using all the labels. We also see very similar moments in language where pre-training on large corpora of text has kind of become a standard in the field. So can we apply something like this in robotics as well? So we would like to move from this kind of closely supervised scenario where we have to provide robots with resets and the tasks that we want it to do, to a scenario where we can just leave our agent in an environment and it will kind of play in it and figure out what are the interesting things to do there, and then practice these skills so that after some time we can just come back and the robot is capable of doing all kinds of different interesting skills. So in order to do this, we introduce dynamics-aware unsupervised discovery of skills, or just DADS. This is the work led by Archie Sharma. The main idea is to use empowerment, so in informational theoretical objective, to simultaneously optimize for skills and their predictability. So we start with a mutual information objective, where here we are maximizing the mutual information between the next state and this skill, here depicted by Z, given the current state. After doing a little bit of math, we arrive at this fraction where the numerator optimizes for predictability. So basically, we're trying to maximize the likelihood of the next state given the current state and the skill that I'm trying to perform. And the numerator is optimizing for the diversity of the skills. So we also want to make sure that all the other skills are not producing similar states as the current skill. So this way, we not only are trying to get the robot to produce very different and diverse behaviors, but each one of these behaviors has to be predictable, meaning that there have to be, it needs to be somewhat sensible. All right, so first we apply this algorithm in simulation in a few different scenarios, such as the ant, the humanoid, and the simple in-hand manipulation task. And we can see that we can discover all kinds of behaviors that are somewhat sensible. So we have the ant that can navigate in all kinds of different directions. We can do the same with the humanoid robot, as well as with the in-hand manipulation task, we can learn how to rotate in different directions. And since we are also optimizing for predictability, we are essentially learning a skill-based dynamics model, which we can then reuse to plan for the skills at test time. So in this case, we just let the humanoid learn all kinds of different ways to navigate in the environment. And now, because we have a model that was used to train the DADS algorithm, we can use this model together with model predictive control framework to just plan to previously unseen goals, to reuse the skills that we learn how to do during DADS training process. So not only we can learn all these different skills, but we also know how to use them at test time. And then we also have the extension of this algorithm that allows it to be much more data efficient and eventually allows us to run it on the real robot. And this will be presented during the RSS conference. This is again work led by Archie Sharma. Here we have a simple quadruped robot that was able to learn how to navigate in different directions. And then at test time, we can repurpose the skills to achieve the goal that we want here, to have the quadruped navigate to a certain goal. And this is done completely unsupervisedly. All right, so to summarize that part of the talk, the key insights are that we can use mutual information objectives to do unsupervised reinforcement learning. We introduce a method that optimizes for both predictability and diversity. And the predictability aspect of it allows us to use model-based planning at test time so we can repurpose the already learned skills. And I believe that this is an interesting way to scale our data collection process where you can just leave the robots unattended and they'll kind of collect the data for us. Right, so during the talk, I addressed these three different parts where we talked about how can we make robotics look more like a data-driven field. And the hope is that if we do all of this and if we do all of this correctly, we'll be able to start making progress by just scaling up all of these algorithms. So one of the avenues for future work that we are looking into right now is basically verifying that hypothesis. So are we at the point where we can start seeing progress from just scaling things up? So one project that we're working on is to scale up multitask reinforcement learning, where we have multiple robots in the real world collecting data for many different tasks. And then we also try to see whether we can have robots do useful applications such as sorting trash by taking advantage of vast off-policy data collected by many different robots and seeing if our off-policy reinforcement learning algorithms can deal with that. And I hope that we will be able to talk a little bit more about both of these works very soon. All right, thank you very much. These are all the collaborators and all the papers that I mentioned in my talk. Thank you.